Okay, it says week 11. However, we are having the last hour of week 10. But we have to be a bit quicker because this is a 14-week course, but we got the midterm as well. That's why we just pass 1 hour early to week 11 and start the new concept, interrupts, guys. Okay, so interrupt is a conceptual subject. I mean, we should first understand what an interrupt is conceptually, okay? Because actually you, for the first time in the previous hour, some of you have felt the need for an architect or concept like interrupt in the previous hour when we had the busy wait. You remember one of your friends asked, was it Ridwan? I think it was Ridwan, right? Ridwan asked, but while, or John, well, I don't, John or I don't remember. While we were waiting for the press event, you remember it was we had a subroutine called wait for key pressed, we wait for key release. We waited. The microprocessor didn't do anything else. However, I mean, the microprocessor doesn't work like that. Your cell phone has a microprocessor, and usually it has single. I mean, it used to have a single core. Usually they have multiple cores nowadays, but previously computers and cell phones had a single core, single arithmetic logic unit. It means so a single core can make a single operation at a second. So it is like while you're writing on your keyboard, while you're just typing on your keyboard, the microprocessor shouldn't have been able to show some graphics or calculate something. Imagine your computer is calculating somewhere in the background, but you're able to do something. For example, it is showing a slide. I'm moving the slides. It is working, but at the same time, Zoom is playing and it's recording my voice. At the same time, it's sending my voice out. But there are not infinite number of microprocessors. So how come it's working? There should be a mechanism to cut different jobs and put them in an order so that the microprocessor would be able to handle multiple tasks once and simultaneously. Actually, that very mechanism is called the interrupts, and it's a very fundamental mechanism for all microprocessors in the entire world. Any microprocessor being able to do two things at the same time uses this mechanism, interrupts. I mean, there are microprocessors still that do not use this mechanism. For example, your, yes, washing machine. Your washing machine is so stupid. I mean, you just give a code, it runs a sequential code, and it just pumps it, waits for 20 seconds, waits for the pump to conclude itself. A sensor outputs something, waits busily for the sensor. When the water is pumped, it continues. So it's a sequential operation. However, for example, the same example, your cell phone can do multiple tasks simultaneously together. So the mechanism for this is called interrupt. And interrupt is actually an automatic transfer of software execution in response to a hardware event. Hardware trigger. By hardware event or hardware trigger, what we mean is an event out of the microprocessor. So I'm not talking about an event that happens in your code. Imagine your code, you're doing something sequentially, you're doing line 1, line 2, L3, LDR, blah, blah, something. And at some point, an interrupt comes and you stopped running this code and you jump to another line of code. When this trigger will come, you don't know because it's not written in the code. It is coming from outside. Somebody has pushed the switch or a packet came. And while this packet came, you were not waiting busily for that packet to come or for that switch. Remember, while you were waiting for that press switch event, the thing that we have seen the previous week, this one, you busily waited. You couldn't do anything else. Imagine a mechanism. We continue to do our job. We continue to sequentially execute the lines of code in our instruction memory. We don't stop. But when the switch is pressed, we stop everything. We jump to another code. We finish it and come back to where we left. And when did it come? When will it come? We don't know. It can come anytime. This mechanism is called the interrupt, guys. So it should be triggered by an external device like a keyboard or printer, or it could be an internal event out of the code. Internal event means in your microprocessor, there are mechanisms to call the interrupt mechanism, but it is not the code. It is, for example, something goes wrong, you have a temperature sensor, your microprocessor's temperature goes very high, then you call an interrupt. So it is something actually coming from the outside of the instruction memory or the instruction set, instructions in your code, okay? Interrupt occurs when hardware needs or can service. That's the definition. Let's try to understand this better. So the second slide is about the busy wait operation we have defined previously. In the previous hour, we have done a hands-on code experience on this wait for press subroutines. You'll remember those. We were doing debugging on these lines of code, and since we have made this R0 point to R4, where you had a line like, you remember, so in R4, we had something like in the top of the code, R4 equals something like port F data register or port F PF4, the single pin map. You remember? So R0 is pointing to, so R4 is pointing there. Sorry, R4 is pointing here. So I'm loading the value of inside. So this is wrong. This is this way. So sorry. So let me just. So this is this way, guys. I'm loading the value inside there. So that's why I'm reading it. I've already initialized this pin that R4 points to as an input port, which is connected to one of the switches. And when the switch is pressed, I can understand it. But while I'm waiting for it, I cannot do anything else. This will run infinitely unless I press the switch, okay? And this code will run infinitely unless I release the switch. So unless press and release the switch, these two codes will run infinitely. I won't be able to continue to the next lines of code. This is called busy wait, guys. Busy wait is a very common element in embedded programming. I mean, you will need busy waits. But while busy wait, you are not able to do anything else. So you are stuck. You are frozen. While doing busy wait, your microprocessor is useless. So we are dreaming about a mechanism which will be able to get a trigger like this, a switch, however, won't stop doing its job. It will be able to run a code while waiting for an outside trigger. Okay? So any questions about busy wait here before I continue? Okay? So this interrupt mechanism prevents us from busy waits. So the most fundamental reason that we design, not we, the first people who have designed the microprocessors have thought of an architecture like interrupt is because they wanted to prevent busy waits, because busy waits is something bad. While busy waits think you're not doing anything, your microprocessor is spending energy, but it's doing nothing. So it's not efficient, okay? So while doing busy wait, we stop everything. We don't want to do that. However, if we create this so-called interrupt mechanism, what happens is, this is your main code, okay? Your main code is running. So there are lines of code. So this is the first line of code. This is the second line of code. So imagine the lines of code are not vertical, but horizontal in a sense. So you're running your lines of code. In line, this is line 10, this is line 11, line 12, 13, 12. At line 14, while you were executing line 14, by chance, you don't know you're executing line 14. Just by chance, somebody pressed the switch. The interrupt comes. Your main code is frozen, okay? Frozen. You don't lose or forget anything about it. You jump to another subroutine. You run that subroutine, you do the job. When you're finished, you come back and you continue from line 14, line 15, line 16, line 17. So it is like going and coming back. So it is like a subroutine jump. You know what a subroutine jump is? When in subroutines, you jump to a subroutine, right? But subroutine jumps are initiated with instructions like BL subroutine 1, sub 1. Well, this is initiated, we don't code, but in line 14, we don't know, we don't have something like that. It automatically jumps whatever the instruction at line 14 is. So it is not related to the instruction. Remember, guys, jumping to a subroutine is related to the instruction because the instruction tells us to jump to the subroutine. But when we will jump to interrupt subroutines, interrupt thread or interrupt subroutine, it will not be related to the instruction. We will not jump because the instruction said so. The instruction will be something totally irrelevant because there will be a hardware mechanism to make us jump there. So it is like you are the main code, you are running your lines, then you're frozen. Time stops for you. The microprocessor runs another code. Then you come back, you open your eyes, the clock is the same, nothing has changed. You continue, okay? Maybe the subroutine changed some variables in the memory, I don't know. But it didn't change anything about the microprocessor. So it is like if you are the main code and if you jump to a subroutine, and if subroutine changes a register, maybe you'll realize it because you made the code jump there. You said BL for a regular subroutine. But for an interrupt, if you're the main code, you don't realize it happens. It jumps there and you come back, nothing changes. Even the registers are not changed. It is like the time is frozen. So that's the difference between, theoretical difference between an interrupt subroutine and a normal subroutine, regular subroutine. Any questions about an interrupt subroutine or regular subroutine? What is their difference, or what you understood, or have you got any questions? I'm sure you have. Okay. Okay. Okay, so this is another pictorial representation of what interrupts are. So this is your main code. This is the main code. You have an instruction here, LDR something, blah, blah, and then STR. Then move, it's a code, I don't know, it's just something, for example, pop, then push, add, anything, guys, sub. So this is a subroutine, okay? Subroutine. While you're running this code, an interrupt occurs. The occurrence of this interrupt has nothing to do with these instructions. By chance, just by chance, some guy pressed the switch at that moment and the interrupt came. We're frozen here, okay? We stop running this code. The microprocessor starts to run a new code, which is called the interrupt service routine or interrupt subroutine. You run this code. When you're finished, you come back. You continue from where you left, and nothing is changed, guys. The registers, nothing has changed. So it is like a time lapse. It is like a science fiction movie. In a blink of an eye, something happens, but you just continue. So the main code does not realize if you've jumped or not, and has nothing to do with this jump. So the program flow. That's why it may occur anytime. So by chance it arrived here, right? Or by chance, it could have arrived in the next instruction as well. It's chance. I mean, if the guy pressed the switch like milliseconds later, then occasionally, by chance, the interrupt would have arrived after the next instruction of the main code. Still, you stop what you're doing, you freeze, you jump, you do these lines of code, then you automatically come back. Nothing has changed. So how come nothing has changed? Because while we are jumping here, we save everything to stack, and when we come back, we load everything from stack. Actually, we don't do this. It is automatically done by the hardware mechanism. Okay, we're going to get there. Those are the details. Any questions?
Hocam yani şimdi şey yaptığı tüm verileri kaydediyor, yeri kaydediyor, ondan sonra geri dönüyor. Anladığım bu değil mi?
Exactly. To the stack. And Actually, be careful, guys. You can save all register values to stack, right? You do push stack and pop stack, but it is not you. You are doing it. It happens automatically. The system is designed to do it. You just create the necessary modifications in control registers so that the interrupt can be accepted. When the interrupt is accepted, they're automatically done. There is a mechanism already hard-coded in the device. That's what interrupt is called. And we are going to see every detail of that mechanism. First, we are trying to understand the theoretical background of interrupts. Okay? Guys, interrupt can happen because of many things. Maybe an input came to one of the pins or multiple pins. We have 8 pins in a single port. We have 6 ports. We have 48 pins in total. All of them can create interrupt and separate interrupts. And in our mechanism, which is very complicated, the interrupt mechanism for ARM-based systems have the best interrupt architecture. That's why we are using ARM. That's why the entire planet is using ARM in all mobile devices, because the ARM has a patented architecture, an interrupt architecture, which can allow many multiple interrupts at the same time, so that little devices like watches, intelligent watches, or cell phones can do multitasking and they can do smart things. That interrupt mechanism is called the Nested Vectored Interrupt Controller, NVIC, which we will talk about the next week. Nested Vectored Interrupt Controller, NVIC. We are going to talk about this. This is ARM's patented interrupt architecture. And in this architecture, it can get interrupts from multiple sources. That's why you can do multitasking from many interrupt sources, guys. Okay? However, for you guys to be able to manipulate these interrupts, there should be certain modifications in some certain control bits. Remember what I told you the previous week. You have learned the basics of assembly. The first half of this course is to learn the basics of assembly. How to write an assembly code, how to execute it, how those lines are run, what is a register, and blah, blah. Well, and what I also told you is, in the remaining part of the microprocessors and in your embedded programmer in your career, what you're going to do is you're going to understand architectures or mechanisms which are attached to your device. And all of those mechanisms or architectures will work by changing some control bits. And similarly, if you want to, in your card, to enable an interrupt, you should first change some control bits so that necessary modifications are done and your system will be able to accept an interrupt. Okay, so we are going to talk about mainly that initialization procedure, which bits to initialize, why, what is the general mechanism and stuff. So we start understanding ARM Cortex-M interrupts, which is the most sophisticated interrupt architecture of all microprocessor architectures in the planet. It's the state of the art. It's the best. I mean, that's why, as I previously told you, all of the best universities and best microprocessors courses are being taught in ARM. For example, in PIC or in some other architectures, you don't have this complicated interrupt architecture. That's why it's very important. If you become a hardware engineer, hardware programmer, and embedded programmer, you will always be designing complex systems which are capable of manipulating different tasks at the same time. For those tasks to run simultaneously and synchronously together, you should have the ability to get interrupts from those different events. So some keyboard event is coming, then you're showing something. These are actually events coming to you. And your main code should be able to jump from one subroutine to another according to those. Because if you've used busy waits only, that would have been, a terrible architecture. Imagine you're waiting interrupts or triggers from multiple devices, and you want to design a busy wait architecture. While you're waiting for this guy, the other guy maybe is crying for help, the other hardware. It won't work. So when you are doing multitasking from multiple sources, you need a sophisticated interrupt architecture. And there are many interrupt sources. Actually, in your card, in this card, where's the card? Where's the card? Aha, bir şeyleri devireceğim şimdi. Kart nerede ya? Kart gitti. Ha, burayı çıkarmışız arkadaşlar. Okay, in this card, guys, there are more than 200 interrupt sources. I'm not kidding, 200. I mean, for each pin, as you can see, there are 48 interrupts. But different than the pins, there are other interrupt sources as well. This guy has a analog to digital converter. So it is like when you connect a sensor, analog sensor, and you are trying to digitize it, so you can create certain interrupts. If the digital value is risen above a value, you create an interrupt. And this way, actually, you can create very nice sound systems with this card. I've seen very nice MP3 players and vocal effect devices with this card. It's very capable. It's a signal processing card, actually. Or you have a timer, which we'll be seeing the week after the exam. There's a timer which can create interrupts. So you can create a timing device, very complicated timing device with this thing, actually, which has different periods, and it can create interrupts. Actually, as I told you, you have more than 200 interrupt sources in this device. Okay. So before getting to these individual interrupt sources, because in this course, I will only be able to, in this syllabus of this course, introduce you the interrupts created by the pins and interrupts created by the timer only, because we only have time for that. However, creating interrupts using the analog digital converter, because you can do signal processing with it, connect a microphone, a sensor, or change some values. You can do even deep learning with this card. Some of my students are doing it on their term project in 4th grade. You can do all of these, but you will have to just come to our elective course, Embedded Systems, the next semester if you want to continue. But in this course, we only have time for the interrupts of the pins and the timer. Whatever the source is, each interrupt source must be configured principally following the same rules, guys. The first rule: each potential interrupt source will have a separate ARM bit. ARM is like arming a gun. ARM means, arms in English is kuvvet, silahlı kuvvetler, arms. I mean, that arms is arming a gun. So you just arm this gun. It's like enabling or starting or making it ready for starting, kind of. It is an ARM bit. So for any interrupt source, you want to create an interrupt from one of the pins, and you're going to connect a switch to that pin. There is a separate bit somewhere in a control register to arm the interrupt of that bit. So you go to the datasheet, find that bit, enable that interrupt. Otherwise, you won't be able to accept interrupts from that pin. Okay? The first thing to do, set the ARM bit for those devices from which it wishes to accept interrupts. Device means the input. So it could be a pin or it could be a device like the timer inside the microprocessor. The first step. Sometimes the ARM bit has an optional second step. So for some devices, they all have, as I told you, there are 200 interrupt sources. You should enable the interrupts for all of them. For some of the interrupt sources, this arming step has two steps, two sub-steps. You arm something in a control register, and there is also this controller called the NVIC. It's a separate thing. We are going to talk about this. There's a second bit there you should also enable. So what I'm trying to say is simply, for some interrupt sources, to arm the interrupt, you change one bit. For some interrupt sources, you change 2 bits in 2 separate control registers. Which control registers? Where are they? For which source? All written in the datasheet. And for the interrupt sources, we are going to cover the pins and the timer. We are going to talk about this. The timer will need only a single step of enabling. The pins will require 2 steps of arming the bits. So the first step for any interrupts, you will change 1 or 2 control register bits to arm that bit for an interrupt. Any questions? No? Now guys, please, soru var. Dinliyorum.
Hocam şimdi burada şey yapıyoruz, yani initialize yapmadan bunu interrupt yapamıyoruz. Bu initialize'i en başında mı yapacağız? Şeyde mi yapacağız? Yine bu tanımladığımız yerlerde mi yapacağız?
Okay.
Değerleri tanımladığımız yerler gibi.
Uh,
Ondan sonra mı gireceğiz?
Berkcan, actually, good question. And there is nothing wrong about it, but let's not call this initialization. It's a part of an initialization procedure, but for this specific thing, we call it arming. So for the sake of following the same literature, let's call it arming, okay? And I'm going to answer your question referring to it arming, okay? Yes, you do it in a separate control register, like initialization. And the answer is yes.
Teşekkürler hocam.
The answer was a yes or no question, right? Okay. And how do we do it? Yeah, we're going to talk about it. First, we are trying to understand what to do, then how to do it. Okay. Any questions about arming? So we just change the control bit. Any other questions? Okay. The second thing for all interrupts, we'll set a priority level. Well, a new concept. Wow. Priority level? Sorry, what? Priority? Did you say priority? Let's talk about what priority is. To understand priority, we should just speculate on how these multiple interrupts are coming to us. I am the microprocessor. I'm running a main code. And I've got many interrupt sources connected to me. For example, there are two switches, PF0 and PF4. And I'm accepting an interrupt from both of them. Okay? Or maybe some other device. Something is connected to port A, or the timer creates interrupts, or the analog to digital converter can create interrupts. There are many interrupt sources. And I've enabled all of them. And they may arrive at the same time. For example, an interrupt came to me. And two interrupts came to me at the same time. Which one to run? Because each cycle, I'm working with a clock in this digital clock. Sorry. So I'm working with a clock. So at this clock point, I was running an instruction, LDR something. I've frozen my main code. And two interrupts came. Which to run? Which to run? To handle this ambiguity, when we are defining, when we are enabling an interrupt source, we will assign priorities for those interrupt source. We'll say, hey, interrupt source, your priority level is 2. And we'll say interrupt source 1. For interrupt source 2, we'll say your priority level is 5. And if they arrive at the same time, we will say, okay, so according to priority level, I get you. I'll tell you which one. Actually, it's this one, of course, but we'll get there. So the higher level is better, more prior. So you may think that, but just we're pressing the switch. It's just so unlikely that they will arrive at the same time. Guys, if you're just pressing switches, yes, you're right. However, if you're a router handling the internet traffic of all the devices that are connected to you, for example, when you're at the school, you are connected to the Wi-Fi of the school, and hundreds of cell phones are connected to it. And you're sending packets at incredible rates. And packets arrive together. And if somebody is watching a video, and if somebody is sending a text, those packets have different priorities. And the video has higher priority. That's why you can watch the video nicely. But if the text arrived there like 1 millisecond later, nobody would have realized it, right? Just like the prioritization in networking, we have a prioritization for interrupts in the microprocessor. How will we set it? Again, there will be a control register to set that priority. And actually, I haven't told you yet, but there will be a global priority level at the microprocessor. We will say, let's only accept interrupts above some threshold level. I will say my threshold level is 3. Only this one will be accepted and this one will not be accepted. And I will be able to change this prioritization global level. These will all be done global priority level or the individual priority value for an interrupt. All will be set by changing some control registers somewhere, which we will learn. Any questions about priority of interrupts? Okay. The last step of theoretically enabling an interrupt, there will be a flag. This is a bit difficult to understand before you actually work your hands on it, but we are going to work, don't worry. You have enabled it, you've armed it, okay? And you set the priority level properly so that it will be accepted. The last thing is, when the priority comes, that device will change a flag so that you acknowledge it. If that device is not changing a flag, you cannot acknowledge it. And you just lower that flag back in your code so that you say, hey, interrupt, I got you. If you don't do this, you won't be able to get another interrupt from that source. So that's the third step. It's a bit complicated, but I'm going to show you an analogy. This is an analogy I use every year. So the ones who have taken the course previous year will remember that one. So these are the third steps I've defined here are these guys. And I'm going to explain them with some analogies. So the first one is to arm the interrupts. So think of the microprocessor as a shop. Okay? It is like shop is open or the door is open because in the shop may accept visitors from multiple doors, right? Right? So different doors are different sources of interrupt. So let's say the door is open. Not the shop is open, but the door is open. The shop's one of the doors open. If the door is open, it's not locked. I mean, not open, but it is not locked. The door is, let's say, not open, unlocked. Somebody may come in, right? Because if it is locked, you cannot. The door is unlocked. Okay. It is arming your interrupt. The second level, the second thing, the priority is like there's a bodyguard which can allow you. So your social status is enough for you to get into that cafe or bar, whatever it is. Because if you have pajamas, they will not let you in. You have low priority. And the third thing is you should be knocking and closing the door behind you. Because if you don't do that, you'll be standing in front of the door and the guys before you will not be able to enter. So the third step is making sure that you enter. So that is an analogy you can remember for these steps. If we don't complete these steps properly, we won't be able to operationalize interrupts in our systems properly. Okay? And finally, something I haven't told you in the previous slide. Your microprocessor should globally enable interrupts as well. So that analogy is, if it's a national holiday, all the shops would have been closed, so you won't get any holiday. So it is not a national holiday. So there's another flag, a single flag in one of the status registers. So finally, you should do this as well. This is not directly related to a single interrupt. This is something global, and this should be enabled as well. If all these conditions are set for an interrupt, and this one globally, you will be able to get an interrupt from that source. We still don't know how interrupt happens, what interrupt exactly is. What we just learned is we can create the so-called event interrupt, which will freeze the main code and jump to a subroutine. And we need these conditions for that interrupt to happen. But where is that subroutine? How do I write it to that subroutine? How do I know that when a certain event occurs, for example, a port F0 switch pressed will ignite a certain subroutine, but another subroutine for another interrupt? How do we handle these? We did not learn yet. We are trying to get into the subject theoretically, okay? Please ask me your theoretical or practical related questions now. Okay. Okay, to arm a device means to allow the hardware trigger to interrupt. Now I'm focusing on the steps. I told you for each interrupt there are 3 steps. The first step is arming the interrupts. Okay? To arm a device means to allow the hardware trigger to interrupt. So it's enabling. We have talked about this. We are getting into the details of it. So just the opposite is, if you disarm an interrupt, you are disabling it. So you won't be able to get any interrupt from that source. Each potential interrupt source has a separate ARM bit. And for some of them, they have separate 2 ARM bits, an optional one as well. We have talked about this. To enable an interrupt source means to allow interrupts for that device. And to disable means to just stop interrupts. So this arming is enabling. And remember that this first step is also related to a global interrupt steps as defined here. And alternatively, instead of disabling an interrupt source, you can disable all interrupts by setting the prime mask register. So arm an interrupt, you arm this bit, and you globally enable all interrupts as well. Non-national holiday, and you unlock the doors of the shop. So somebody will be able to enter at some time. Arming. How to set the global interrupts? I mean, how to set the individual ones? We'll get there. How to set the global ones? Next slide is, we have a register, guys. You remember the register bit? So we can disable or enable all interrupts by setting the prime mask. Here, there's a prime mask. It's here. There's a register. The E bit, I bit, is the least significant bit here. If you change this bit, you globally enable or disable all the interrupts. Okay? How to change it? Which instruction to use? We will get there. Okay? I'm trying to show you where architectural wise this register and so-called bit is. Okay? It's somewhere in the functional registers. And also, we have to set the ARM bits for the interrupt source individually. Arming needs, as I told you, sometimes a total of 2 bits, 2 steps instead of 1 bit. The device ARM bit, which is true for everyone, and the NVIC enable bit, the second control register for some of the devices. And always remember, this should also be enabled. This guy also be enabled. Okay? So enabling an interrupt is usually a single bit on the interrupt side, but sometimes 2 bits in 2 separate control registers, plus the global interrupt bit. Okay? I know it's confusing, but you're going to, when you get this, we are going to understand what interrupts are. How to set the priority? I told you there are 2 concepts about the priority. My individual priority and the priority level. So priority, the analogy I made to priority in the shop example is how well I am dressed, because I am the customer coming into the pub. I am an interrupt arriving. So will the bodyguard let me in? It will check my, etiquette, my dressing. If I'm well dressed enough, it will let me in. So I have a value for this nice dress I've worn. Imagine I'm dressed in a level of 2. If the interrupt level, priority level of the bodyguard, which the boss have told him, is proper, he will let me, the bodyguard will let me in, or he will not, bodyguard will not let me in. He will just keep me out. This is called the priority threshold, global priority threshold, and my own priority level. So the global priority threshold is called the base pri, which is also registered in its function registers. So you see, guys, we have a register bank here. We didn't know what these were for. Well, these are for this. Actually, they all have purposes. We will write the base pri, the global priority level here. So this will prevent interrupts with lower priority, but allows higher priority interrupts. What does a lower priority means? Is it a lower value or higher value? It's the opposite, actually. For example, if an interrupt source, my customer's dress, I'm the customer, my dress is a value. Let's forget it. I'm going to, for example, my value is 1. I'm a first class guy. If the priority level, global priority level is 3, then all customers with priority level 0, 1, 2 will be accepted. But 3, 4, 5, 6 will not be accepted. Okay? So the higher priority value, better the priority level. Sorry, the lower the priority value. So this is a low value, I'm sorry. Lower the priority value, 0, 1, 2, better your priority is. So it's opposite, okay? So when the priority level is 3, so base pri is, if the base pri is 3, 0, 1, and 2 are accepted. If the priority level is 4, 0, 1, 2, 3 are accepted. What if the priority level is 0? Is it nobody accepted? No, it is an exception. If the base price is 0, then everybody's priority is accepted. It is like if it is 0, the bodyguard does not care about your clothing. Any clothing is welcome. You can come in with your pajamas. Okay, where is the priority of an interrupt is written? To which register? Where is that control register? We will get there. Any questions? Okay. Vaktimiz var. Bunları anlatabiliriz hala. So how to set the priority levels? Actually, the base pry, as you can see here, the base pry is a special function register. And you can see it in Kale here, the base pry value here. How to change the base pry register? Actually, move special register, new instruction, modify special register, base pry will be set the value of R0. And if I have a value to R0, it will be set. So what is the priority level of the system if I loaded this value, D0? Guys, it's a bit complicated. If you go to the datasheet, this is the base pry. These values are not used, reserved, and these are not used as well. So if they are reserved, they are by default 0, 0, 0, 0, 0, 0, 0, 0, 0. And if I write D to this R0, what is D? What is D in decimals? I cannot hear you. What is D? 13, thank you. What is D in binary?
1, 1, 1, 0.
It's
1, 0. Bir daha 1 var, ondan sonra 0.
But if there's a 0, that means it's an even number. Don't forget this. And 13 is an odd number. So could it be 0, 1? Maybe.
Evet.
Okay. So what I'll be trying to write, what I'll be trying to write. So I have this value in R0, right? And I'll be trying to write this value to here. So I'll be trying to write, if this is 0D, I'll be trying to write 0, 0, 0, 0. Here it is. No, this is 1, sorry. This is 1. This is 1. 0, 1, 1. And zeros, of course. Because in base pry, this is what I do. I'm writing this value here, right? So guys, remember, we cannot change these bits. So even if you try to write 1 here, you cannot change it. It will be 0. This is a read-only place. You cannot write it. So this is 0 again. So what I could write was 1, 1, 0. What is this 1, 1, 0? What is 1, 1, 0 in binary?
Dokuz değil mi hocam?
It's 6. Only 1, 1, 0. It's 6, isn't it?
Evet hocam, 6.
And with this operation, you've made the global priority level to 6. Now, having said that, let's do another example. I'm going to change the code. So instead of D0, imagine the example was not D0, guys, not D0, but let's say it was it A? Excuse me, C0.
C.
Yes, you understand what I'm trying to do. If it was C0, would it make a difference? No, because it would have been C0. These would have been 0 and 1, 1, 0. This wouldn't make a difference. So be careful, guys, about these reserved bits. Writing D0 or C0 will make it 0 in the end. Because the definition of the priority mask register is such that it is only using the bits 7, 6, and 5. So the value that you should feed into base pri should be accordingly. How do I know this? I know it from the datasheet. Just open the datasheet, find base priority mask register, and you'll see that it is 110, guys. And to enable all interrupts, to change this bit, the I bit here, to enable them, you call this function, okay? It changes that bit, instruction. Okay, so how to globally enable the interrupts and how to globally set the priority. So for example, let's make another example here before we finish. Imagine, I'm just going to so that imagine I'm loading not this value, but 10. What will the priority level be? Any guesses?
1 hocam.
Careful. Zero. Because this one will hit the reserved part. Isn't it so? Bir diyen kimdi? Alp sen miydin? Kimdi bir? Yeah. Cahit sen miydin?
Evet hocam ben.
Okay, but now you understand it's zero, right?
Evet hocam.
Okay. That's a trick. That something you should be very careful about. So guys, the priority level will become zero. Sorry. The priority level will become zero. And what happens if the priority level is zero? Every priority is accepted, right? Because it said so. Okay. So I think we are finished. We now know how the global priority levels are set to accept priorities. Next time, we are going to be talking about triggering the interrupts. And we are going to learn the entire process of modifying the card so that we'll be able to get an interrupt. Any questions?
Hocam ben bir şey sormak istiyorum.
Please.
Önceki slaytta.
Hı-hı.
Burada MSR ile base prior'ı ayarlarken diyelim ki 8 bitten daha fazla bir veri var elimizde. Ne olacak?
Okay. Well, the rule is the reserved bits are read-only. You cannot write over them. They are always zero. So let's try something. Okay, let's try something. You tell me the value. Okay, you tell me the value. Nasıl sileceğiz ya? Screen. Yes. You tell me the values. What to load here?
Mesela 1AC0.
Okay. Okay, you want to load. So first you should load it to R0, right? So instead of this value, I'm loading 1A. You said C?
Evet hocam.
You say C. So since R0 is a 32-bit register, and you have written a 16-bit value, how do I know that it's a 16-bit? Hexadecimal 4 bits. Each hexadecimal bit is 4 bits. So 4 hexadecimal bits, each 4 bits, 16 bits. This is a 16-bit number. So the first, let me just move this guy here. So the first part, so this R0 is here. Actually, what you have loaded is actually this 0000.1A C0. So you have no problems with it. So what you're writing is 0000000000000000. This was this part. Now this is 10001. This one. This A 1010. This is A. Okay. This is 1. And this one is C, which is 1100. This is C, which is and 0. This is 0. Well, doesn't matter, guys. Whatever you put, they will all become automatical zeros because you cannot write them. So in the end, you had written 1, 0. That's why it is 6 again. The reserve bits, you cannot change. They are 0. Simple as that. You just have to know which bits to write from the datasheet. Okay?
Tamamdır hocam. Teşekkürler.
Tamamdır.